Okay, so we were talking about this scenario that we see this thing in nature, that our light is gradually going up, decreasing the angle, and then when it falls down again, the angle increases. So in this range, from plus 90 to minus 90, we should deal with the light source. Well, actually, the gradual increase or decrease of the amount of light we see. Now, if you look at the model that we had for the ambient reflection, we have intensity of the light source times the amount of light is being reflected by that particular material. We'd have a similar sense of calculation for this one as well, right? For diffuse, we'd have the same set of thing, because the color of the light and the amount that it reflects should also matter. But along with that, we should also include this factor, which will tell us how much light we will have. So the formula for this is going to be something like this. ID, intensity of diffuse reflection, is going to be intensity of the light source times the amount of light that's reflected by the material for diffuse reflection times cos theta. Okay, because this cos theta will tell us if the angle is low, then it should give us high reflection. So for example, right at 0 degrees, what would be the value of cos theta? 1. So we'd have the entire reflection right there. And if the angle increases from 0 all the way up to 90 degree, we will adjust accordingly. So if we have 90 degree, cos 90, we'd have 0 contribution. If we'd have cos minus 90, then also we'd have 0 contribution. So that's how this would work. However, we need to understand that this cos theta is not going to work properly, because there can be scenarios like, let me draw a very simple, crude figure. Let's say this is our Earth, and here we got the sun. I'm not drawing for scaling. Okay. So the setup is something like this, that we have this light source, we have sunrise, and then we have sunset. Okay. So if you're looking at any given point, let me draw a surface, a flat surface over here. So let's say right over here we have a point P, and if I'm to look at this scenario, let's say this is when the sun is starting to rise. We have the entire light at noon, and then it falls down again. This is sunset. But what happens when you go into the night? For example, over here. The angle that it makes with the surface normal is actually more than 90 degree. Okay. So if it goes more than 90 degree, then what happens? You get negative values. Okay. So if you have negative values over here, intensity of the diffuse reflection becomes negative. That means that you're actually taking light away from the scene. It's not even 0, it's minus. Okay. And a light source, or any material, like this surface, it can reflect light. Okay. Or if it acts as a light source, for example, the projector light over there, it can act as a light source. It emits light. So a surface can emit light, it can also reflect light, but there is no surface that will take away light. Okay. So if you have something as negative like this, because it's more than 90 degrees, it's actually going to eat out light, subtract light from you, which is not really possible. So you're not going to do that. And that's why we cannot use cos theta. An easy solution that may come to your mind is that since we cannot allow negative value, why don't we use absolute value then? Can we do this? We cannot do absolute value because, let me see if I can do it over here on full plot. With absolute value, this is how the curve would look like. So if you go after 90 degrees, then suddenly what happened? You'd start to get more light because it's going to be positive. Okay, you can do that. What we need to do, this is what's going to happen. This is how the curve would look like if you apply absolute value. We don't want that to happen. We want flat lines. Then we want a cos curve. Then we want flat line. Because after 90 degree, what you want is total darkness that would stay at 0 all the way. So from plus 90 to minus 90, this is where you're going to get light. From plus 90 all the way to minus 90, this is where we'd have light. And after that, if you increase the angle or decrease the angle, it's going to stay 0. We want to flatten it out just like that. Okay, so how do we do this? If it's after that, we can have this thing again, but that's after a full rotation, right? So this is 0 degree, this is like 90 degree, and then we go into 180, 270, 360. Again, we can go into 90, then this is fine. But after you complete a 2 pi rotation, then you can go into this part again. Let's say sun rises, sun sets, and then sun rises on the next day, sun sets, then sun rises on the next day. If you keep on increasing the angle like that, if you're going for a continuous range, then these things are possible. Then you want to model it like that. But the sense is you cannot do something like this, or you cannot do something like this. These things are fine. So what we want to do is use a different function over here, not just cos theta. We are going to use a max function, and in a max function we can pass more than one argument. The idea is that max will return the maximum value from there. So if you put cos theta and 0 as two arguments, what would you get as max? Yeah. So when you have negative values for cos theta, what's going to happen? You're not going to get 0 anymore. You will get 0. As soon as cos becomes positive, you're going to pick the positive value because that's more than 0. Is this thing clear? Okay, so we're going to rewrite this. Now we need cos theta, right? So we're going to rewrite this because cos theta, we need to calculate that. We are going to rewrite it in a very simple way. We will write it as max of L dot n. What do we get from there? The cos theta value. Okay. And in practice, what we do is we deal with unit vectors. So usually what you'd see is we are, L dot n, that would give you L n cos theta. You need to get the cos theta only. So you need to divide this by the magnitude of L, the magnitude of n, and then 0. So this part, the first argument, is nothing but cos theta. The only reason we rewrite it in this way because we are dealing with vectors and it's easy to implement in that fashion. So this is about the intensity of the diffuse reflection. Okay? So if you look at a total example for working this out, we got the intensity of the light source. So like the previous example we had, we will give you some intensity of the light source. For example, over here, we'll give you that. What about this rho A? If you're looking for the bronze material, the same bronze material, do we know rho D? We need to know this, right? Where is this rho D? Rho D is this. So if you're doing it for the red color, we'd be picking 0.714. If you're dealing with the blue color, we'd be picking up 0.181. Okay?
Sir,
yep.
in this table, what is last column?
The shininess?
Where is blue or?
No, it's a totally different thing. We'll come to that. It has something to do with the specular part. These two things, they go together. So I'll talk about that. So for now, the stuff that we're dealing with is just these two, ambient and diffuse. But is this thing clear? We can read up these values from the table to get the ambient reflection or the diffuse reflection coefficients and then plug them into our model. So that's two parts. The ambient reflection and the diffuse reflection for this particular model. Now the more difficult one is the shiny part. So if you're going to Blender and look at our test render, okay, you can see that there are some shiny parts right over here and up here. Okay, depends on the material. If you have a very matte material that doesn't shine, you won't see these things. But if you're modeling, let's say, a car, the body will be polished and you'll see a lot of shine, a lot of reflection right over there. Now, if you're looking at something like this material, this white plastic board, it also has a lot of shininess, and that's quite apparent from the reflection of the light source. There will be a bright white light which makes it somewhat difficult for us to see the objects right there. And that thing moves along with the viewer. So when I'm here, I see the reflection here, but if I move away, that also moves away with me. Okay? So even when you're sitting right at your desk, if you move your head, you'll see that the white light is moving with you. So how do we model this thing? To understand that, let me draw a figure over here. Let's say we got a light source somewhere over here that's going to shine light, and it's going to drop on the surface, which is going to reflect like this. Okay, so let me put up the labels. This is the light source, and this is the surface normal, let's say. And okay, actually let me make it a little bit shorter. Okay, so that's going to be the reflection. Okay, so we can say that this is our L vector, and this is our excuse me, this is our R vector. That's the reflection vector. So whatever angle we have over here will be the same angle we have over here, and this is our point P. Okay. Now what's going to happen is that since this light source, it moves along with our head, along with the viewer, so it really depends where the viewer is. So if the viewer is over here, or this viewer is over here or the viewer is over here, it would make a great difference. Right now, if you try to imagine that the viewer is placed in a way where the light reflection hits along that line, that the viewer will see the full reflection. It will be really bright. But if the viewer moves away from the line of the reflection to somewhere over here, then the viewer will see less amount of light. Okay, so this is not really with the normal, but more so with the reflection vector. Okay, as the viewer is moving away from the light source, so if I try to align myself with this thing, I'd see a very bright white light right at the center. But if I move away, then the intensity of that will diminish a little bit. So this thing needs to be an angle, and I'm going to draw that as well. Okay, so if we put up a label over here, this is going to be our V vector, and let us put a label that this is our point V as the viewer or the camera. Okay, so what I'm saying is right over here we have a new angle, and let us give a different label. Let us call that phi. So based on this angle phi, it really depends of how much light is going to be reflected back as the shiny component. Okay, so let us look at a quick example over here. Let us go into the object mode and the rendered mode, but before doing that, let us look at the setup. Right now the viewer is over here, and this is our light source. If I go into the rendered view, okay, if you look from a different angle, do you see the reflection? I mean, this is where the light source was, and it looks really bright right here. But if I move away, that reflection moves along with me to different points. Okay? So right now I don't get as much bright reflection as I had when I was at the right angle. So maybe this is the right angle, and this is where we get the brightest reflection, but otherwise we don't get that. That's the point I want to make. So yeah, something like this. Now to model this thing, what we need to figure out is this reflection vector, because if you don't know that, you cannot find out this angle between R and V. So what are the things we know already? Do we know this L vector? Or can we calculate this? L is a point, that's the light source. L minus P, that will give us our L vector. Do we know the N vector? L minus P is this L vector. That's easy to compute. We know the light source, we also know the point, so we can find out the vector. Do we know the N vector? And yes, we know that because it's on a surface. We can calculate the surface normal using cross product. That will give us the surface normal on the surface. So N is also known somehow. Do we know the V vector? From the point to the viewer, do we know this? V minus P. V minus P, we know that already. So this is also known. What we need to find out now is cos phi. And cos phi can be found if you know the r vector and the v vector, and then you do the dot product in between them. Okay, we have just done this part right over here. This is the dot product thing. You just bring these two things over here, that gives you cos theta, and if that's the case, then you can also find cos phi. It's just that we do not know how to find the r vector. Is this problem clear? We need to find out this r vector. What we do know over here is that this vector, this r vector, will create the same angle that L vector creates with n. That's the only thing we know. Okay? So we need to figure out this r vector. If we can do that, then we can plug that in over here to compute cos phi. If you need to get the cos phi out of that, it's easy to do. You'll just do cos inverse of this thing, and then you'd find phi. So we'll see if we need that. Actually, we won't. So finding the r vector is the main challenge over here. Otherwise, things are really very simple. So in order to do this, it's going to be quite a few things you need to consider. Let us look into this in this way. That if I draw a perpendicular on this thing, okay, what I'm going to get is the projection of vector L on vector M. It's a vector projection. You drop one vector on another vector and then you find out the length. It's a scalar component vector projection. If you want to find a vector that goes along this line, that's that. Okay. So once we find out the projection over here, why am I trying to find out the projection? Because I want to construct a figure that goes like this. So once I find this projection, the length of this projection would be the same over here. If I draw a parallel line, if I draw a vector L over here, can we do this? The length that I find over here would be the same length over here. If I project vector L again onto the same thing, that will give me the same length, right? Okay. So check something out. Like, I mean, if you have this figure, R plus L, what's that? This is the law of parallelogram in vector. That if you have two vectors, let's say R and L, and if you add them up, the resultant vector will be the diagonal of the parallelogram formed by R and L. Okay. Let me draw it in a different way that is probably more familiar with you. Like if I have a setup like this, let's say I have vector A and some vector B. So you got vector A over here and we got another vector B right over here. If you want to add them up, what you need to do first is you need to form a parallelogram. So you need to find out a vector that's parallel to B, and you'd have another vector that's parallel to A, something like this. Okay, and once you form the parallelogram, the resultant vector can be computed as the diagonal that goes like that. So that's vector A plus vector B. Is this thing clear? So if you understand this part, Let us go back to this previous picture. We know vector L, we know vector R. So this is going to be the resultant diagonal that we can find out, right? So this is where we can say that if we have vector n, let me change the color. If you have a vector n, you can find out the unit vector for n as well. How do we do that? Just like that. Okay. If you divide a vector by its magnitude, you get the unit vector. So what's the beauty of a unit vector? You can multiply a unit vector by any length, and the resultant vector will be a vector that goes along that line but has a length of that much unit. So for example, if I have 50 n hat, that will mean that I'd have a vector that goes along in the direction that n goes, but the length of that vector is going to be 50. So if you know this thing, and let's say I multiply this with any k, then we can say that the length of this vector is k, and it goes in the direction of n. Okay. Where am I going with this? Is something like this thing. So let's say I have measured that the length of this whole thing is, let's say, k units. This whole thing from P to this point, let's say that the whole length is k, then we can say that this vector that goes from P to all the way to this point, let us give it a name, let's say that this is n. We can say that the length of that is k units, and it goes like that. So let me write it down in this way. Pn vector, we don't know this point n, that's the problem. Pn vector is equal to k n hat. Can we say this? So the problem at hand is really, we want to find out the R vector. That was the real problem, and it's possible now if we can take this L vector and put it on this side, but even to get there, what we need to know is this k value, because we can find out this n vector, unit vector n quite easily by dividing n by its magnitude. We can find this out. We just don't know this part. Once we know this part, we can transfer L from this side to that side. Are you with me so far? If I lost you, then let me know. I can track back and we can go from there. So this is where we need to find out this whole length, and in order to do that, we constructed a diagram like this is L, this is L. So if you project over here, this is the length, okay? So let us try to find out the vector projection, and in order to understand that, let me go to something very basic. Let us go for a trigonometric construction. Imagine that this is a right angle triangle, okay? And let us label them. Let's say this is the base, this is the perpendicular, and this is the hypotenuse, okay? And here we got theta as angle, okay? Our sine theta, cos theta, and tan theta, they are all based on these things. What's sine theta? P by H. What's cos theta?
B by H.
B by H. And tan theta is P by B. Alright, so if that's the case, we can also write them in a slightly different way. We can write them as P equal to H sine theta. And we can also write B equal to H cos theta. Is this clear? Alright, so armed with this knowledge, let us look into a vector world. Can we apply the same thing? Okay. So let us consider that we got a vector like this. Let us say that we got a vector A and we got a vector B in this format, and I want to find out the projection of B onto A. Okay, what does a vector projection do? We are going to drop a vector onto this one. Okay, then we get a new vector that goes along in the direction of A, but will have the length of this much. Okay. Vector projection is like flattening it out. You're going to drop this vector and you want to find out what's the component along this direction. So we want to find out the length over here. So if you understand this part, that B is equal to H cos theta, help me out in this scenario with A and B vectors, and let us use a similar label over here. Let me just call this one theta as well. Okay. How can I find out the length from here to there? How do we do this? B by cos theta. Okay, we'll get there. First of all, let us write it down in something that we know already. If you do A dot B, what do you get? We wrote it a few minutes back in our previous class. This is going to be AB cos theta. Is this clear? So what are we trying to find out over here? We are trying to find out this part. Okay, we are trying to find out this part. And this, as you can see, is H cos theta right over here where this is H. And what's H over here? That's B. Actually, that's the magnitude of B. Okay. Are you guys with me? So this H over here is the magnitude of the hypotenuse, of this vector. So if you take the magnitude and multiply that with cos theta, what do you get? We get the length of this thing. Okay? Do we have it over here? We have that thing in parts. Like we have this part already. But it also comes with a baggage. Comes with the magnitude of A. So what do? We take A vector over here, and that leaves us with B cos theta. Let us try this out again. So I think I lost you guys. is this part okay? That we can write the dot product as AB cos theta. Okay, so that also means that we can, this is a scalar value, A is a scalar, magnitude of A is a scalar value, magnitude of B, that's also scalar value, cos theta definitely is a scalar value. So what I'm trying to do now is I'm trying to take this vector A and put it down here. So what's going to happen at that point? I'd get B cos theta. So what's actually B cos theta? This is the magnitude of B, and then we have cos theta. So if you look at this particular scenario, the magnitude of B is the length of this hypotenuse. So if you go back here, H is this hypotenuse, and H cos theta is what? Is the length over here. Okay? So that's what we got. We want this length, and that's why we do A dot B and divide that by the magnitude of A. So in other words, the vector projection, this thing, can be written as A hat dot B vector. Why A hat? Because we are dividing vector A by its magnitude, that's why this is A hat, dot product with B. So simply put, how do you project a vector onto another vector? How do I project vector B on vector A? I do a dot product of vector B with the unit vector A. That would give me the vector projection onto the second vector. Do we understand this part? We do know A. Like we were talking about two different vectors. Let me redo this part. The scenario that we have over here is we are talking about vector dot products. We are given two vectors. We are given A and B. A goes from here all the way to this point. So let me write it down in this format. So let's say this vector A is A minus B. And what's B? Yeah, B minus B. This is something we know already. What we don't know is the length over here. If you drop vector B on top of A, what's going to be the length? This is something we don't know. Yes, we do know the entire length. We know the length from here to there. We know the length from here to there. But this is the part we didn't know. And that's what we figured out with the formula A hat dot B. Okay. Probably the reason you guys got confused is because of my bad choice of labels. I'm writing B as the base over here, again B as the hypotenuse, but that's not what I meant. The hypotenuse, regardless of its label, is this one, and the base over here is the length that we're trying to find out. Now, if this is all right, then we can go back to this part. Let me make a copy of this. Okay, so we got this set up. What I'm trying to do now is I need to find out this length, because if I can do so, then I can also say that it's the same length over here. And once I know this entire length, which we're calling K, we can plug that into this formula. Okay. So can you tell me the length of the pink thing that I just wrote down? with vectors. This should help. I only want to find out the length of this pink part. And as for hint, let me tell you that this is vector A. We got one vector over here. L is vector A, and we are trying to project that on this long vector. This is the N vector. We are going to project L onto A, and we're going to find out the length over here. We already know the L vector, we already know the N vector. We want to find out the pink length. L minus P gives you the L vector, yes, we know that. And we also have the N vector. Just we need to figure this part out. We have a very similar problem over here. We have a vector B. We are projecting that on to vector A to find out this length. Yes. And if it helps, let me redraw this thing right beside it in that way. So let's say we got this B vector, and we have a long vector, we are calling that A. We want to do a perpendicular projection like this, and what we try to find out is this part. Well, let me do it with the same color. So seems you guys are lost. So we have these two vectors, and what I said is that this can be written as A hat times B vector. So given this scenario, to find out this pink part, what should we write? So instead of this A vector from here to there, what do we have? This is our surface normal vector, right? That's the N vector. So instead of A, you're going to write N hat. And what do we have as B? The L vector. So it boils down to just this. N hat L, the dot product of these two things. And if we know the length of this thing, this would be just the same. So we can actually say that K, this entire length from bottom to top, is going to be twice as much, right? Which is 2 times this. Is this thing clear? The entire length from bottom to top is 2 times this thing, and one of this is N hat L. So once you know this thing, we can say that R plus L is a vector that goes from here to there, and that's 2 times N hat L dot, that's the length. But if you add 2 vectors, what do you get? A scalar or a vector? If you add 2 vectors, you get a vector. You get a vector in this direction, right? So we get the length of the vector, and the direction of the vector is this. Okay. So the second half is not a dot product. This is the length of the vector, and this is a vector along that direction. So if you put everything together, you get another vector for which you have a length. So down here we have a unit vector. So if you realize this, let's say we got a long vector. Let's say this is 10 units long. Okay, the unit vector will be 1/10 of it. We only need to divide it by the magnitude. And now we can make a vector that's, let's say, 5 units long just by multiplying with 5. We can make a vector that's 6 units long if you multiply by 6. That's why what we do is we find out the unit vector, that's n hat, and then multiply with whatever length you need it to be. Okay? That's how we have constructed this. And this allows us to sort of rewrite this. We're finally coming down to the reflection vector. This can be written as what? To n hat dot L multiplied by the n hat minus L hat. Is this thing clear? Do we know how to add two vectors? Do we know how to subtract two vectors? Sure. This thing over here, right? Okay. Okay, so, all right. Let me redo the whole thing, but I'm going to rotate this around because I think that's going to be easy for me to draw in this fashion. So let's look at a very simple case. Let's say we have a horizontal line, okay? And we have, not from here. Let me draw another reference line over here. That's a perpendicular. And from there, I have another line. So let us put some labels here. Okay. So layer 1. So the labels that I want to put over here, that this is our L vector that goes from this point, this is our point P, to some other point, this is our point L. We have a L vector like this. Now another thing is we have a point P, and somewhere over here there's another point N which we don't know, right? This is not known to us. But since we know P and there is this point N, we can define a vector like so. That's a vector that goes from P to N. So the length of this vector is from here all the way to this. What's going to be the unit vector? The unit vector, you're going to divide it by this much, and maybe this is the unit vector, n hat. So n hat goes in the same direction, but it's a different thing. Okay? It's a smaller vector. It just has unit length 1. Okay? So assuming that the length of, let me just write it down as an assumption, the length of this is 10, then n hat's length is obviously 1. We know that the length of a unit vector is 1. So that is just to give you an example. Now what I'm trying to find out is if I drop this vector PL or the L vector on top of this n vector like this, what's going to happen? We will have a new vector, and let me draw this over here. We will have this new vector that goes like this. Okay? So if you look at this vector from P all the way to this unknown point, okay? Let us say that this point is x. Let's say that this point is x. I want to find out what this vector Px is. Or what's the length of this vector Px. There are two different things, but if I can find one, then I can obviously find the other. Let's say if the length of this Px is k, how do I define vector Px? We can say that this is going to be k n hat. Is this thing clear? Because we can find out a unit vector that goes along Pn, that's the n hat, and you can multiply that with k to get this vector Px. So this is where you can bring in a little bit of trigonometry. If this is your angle theta, then how do you find out? Let us forget that these are all vectors for now. Let us just jump into trigonometry for a bit. Treat them as points, P, L, and X, and tell me what's going to be cos theta. Cos theta is base by hypotenuse, right? So what's the base? Px divided by PL, that's cos theta. So let us go the long route. I'm going to write them down. Cos theta equal to base, which is Px, divided by PL. We can write it that way. Now, the problem that we have right now, this Px and PL, they can be treated as points, but we really have vectors. So this is a scalar component, and if you want to play with this, you cannot just write them as vectors. You have to have scalar values as well. So what's Px is nothing but the length over here. What is PL is the length of this vector L. So this is easy to write, so let me just write this down. Okay, and for now, for the sake of labeling, let us say that we have an x vector, and we want to find out the length of this vector x. How do you do this? You transfer this over here. So what's that? Okay, that would give us what? The length of x. Now the problem is I don't know what this cos theta is. How do you find this cos theta? Well, we got the vectors. We got this n vector, we got the L vector, and that would allow us to find out the cos theta. So we wrote this before, and I'm going to reuse this part. We wrote it over here, that A dot B gives us AB cos theta. So when we drop down over here, instead of cos theta, we can actually write down, this is this part, this cos theta will be L dot n, because these two vectors are known, L and n is known, divide them by the magnitude of L, divide that by the magnitude of n, equal to what? The length of this x vector. Now what you'd notice is that these two things can be crossed out. They are the same. What do we have over here? the vector n divided by the magnitude of vector n, which is actually what? N hat. So this can be written, and let me write them down over here. This can be written as L n hat. Is this thing clear? Okay. So now to finish this up, let us come with another vector. So, one of our previous class I told you, and you have learned that in physics, that vectors, they don't have any origin. They only have the length and the direction. So we can take this vector over here and copy paste that over here or over here, anywhere. It's the same vector. So I can pretty much put this vector over here like so. Well, something like this. I'm not drawing for accuracy, but you can probably understand that this is a copy. So if I have a vector like this, it's going to be the same thing. If I drop it off on over here, then if the length over here is k units, then this part is also k units. It's the same vector, right? It's just a shift of that. So the entire length from here all the way to this point is what? This pink line represents this thing. Is this thing clear? And that's what I wrote down over here. If I know the length, then I can find a vector that goes from point P all the way to this point. It has the length of this much, but it goes along the direction of vector n. So that allows us to find out yeah, that's R. And believe it or not, I mean, that's what I tried to make it. Okay. Alright, so that brings us to the R vector, and if you have the R vector, we can proceed from there. Is this whole setup clear? That now we know the R vector, and the only reason why I need this R vector is because otherwise, without this R vector, we cannot compute this angle phi. Everything else was known. We didn't know what this R vector was, and just to get that, we had to go through all these calculations to get vector projection and to then scale the vector to that length. So finally, once you have the R vector and you already know the V vector, how do you find out this phi? You just do the dot product as we did before. This is going to be R dot V divided by magnitude of R, magnitude of V. With that thing done, we will have cos phi. Are we okay so far? Now comes the fun part. Let us go back to full plot one more time. We know how cos x looks like, right? This is cos x, and I'm going to add a few more functions. But with a different color. That's cos square x. Let us add another function over here for cos cube x. Okay, and one more. Cos, let's say 10x. Okay. Do you see what's happening? I mean, they retain the same shape. The coarse curves, they retain the same shape. It's just that as you increase the power, the band gets narrower. They all end over here at minus pi by 2 or plus pi by 2, but they're getting narrower like that. It covers a smaller range. Okay. So this is something we want to model into our real life. Like we need that. And let me show you why we need this thing. Let me get out of this. If you're looking at this particular model, we're building a material for this. We can control the specular intensity. Let me bump it up so that it is really shiny. You see, here we have another parameter that's called hardness. How hard this material is. So let me zoom it up so that you can see the parameters down there. So that's the part that I'm talking about. The hardness. Okay. If I reduce this hardness, this is right now 50, okay? If I drop it down to 10, it will look brighter, but it will cover a broader area. However, if I bump it up to, let's say, 100, see, it becomes narrower, but the shine over here is really very bright. It has a small area to focus. Okay? If I increase this hardness, see, it becomes smaller and smaller, and if I bring it down, it becomes larger. So this is not to say that this object is more shiny. It's actually less shiny because the point of shininess is becoming more and more vague. Okay? If you consider two different materials, let's say a silk fabric, compare that to a metal. I'm not wearing silk, so I can't really show that. But if you look at this metallic key ring that I have, it shines in a very small area. The very bright shine is actually in a very small area. And if I tilt it, you'd see that the shine goes away and comes back. Whereas, compare that to this plastic smooth cover that we have, it shines in a bigger range, but the shine is a little bit less bright. Okay. So for plastic-like material, you'd have less hardness, and for metallic material, you'd have very high hardness, because that would allow you to make things narrower with higher shine. How does this thing have any sort of relation with the coarse curve? Because this way we can control exactly that phenomena. If that angle of spread if the angle of spread is low, if you have high intensity coarse curve like that, like a high exponent coarse curve, what you'd see, let's say this is 0.5, right? Right over here, 0.5 in radian though, you see we'd have low values, but if you had low degree coarse curves, low exponent coarse curves, they'd have higher intensity. Okay, so depending on the exponent, you can actually narrow down the band or you can expand the band. And how that relates over here in this picture, let me see which layer I am in. Okay, you can define materials in your own way. So let's say I'm dealing with a soft sort of material, then I can say that the range in which you can see this thing is something like this. Excuse me for a bit. Sorry about that. Let me draw that with color. I think that's going to be better. So for some material, maybe the range that I can cover will be around this, everything will be around this reflection thing. So maybe that would be narrow. Or for some other material, it can be bigger than that, so that we can see more of it. Okay? Now this is in your control. How small a range you're going to cover or how big a range you're going to cover, this all can be controlled with just tweaking the cos curve that we have. If you go for higher exponents, you can cover narrower range. If you go for smaller exponent values, like 2, 3 or something as such, or even 1, then it's going to be much wider range. So just to show you that you can also go for, let's say, 1.2. Well, this is how it looks like. Oh, that's 1 already. So if you go lower than 1, then it becomes even wider like that. Okay? So we can control this, and that's the thing you'd find in this part. This is the shininess part. Shininess is actually the exponent. What we are dealing with, let me write down the formula because we're pretty much towards the end of the class. We want to find out the intensity of the specular reflection, and this is going to be IS times rho SP times, and this is where we need cos phi we will put an exponent up here that will help us control the type of material. If you want higher exponent, that will make it harder. If you put lower exponent, that's going to be lower. This is like cos square theta or cos cube theta, something as such. And this F is actually the shininess that's in the table. We call this shininess, or it's also in Blender known as the hardness. So that's what you can control right over here. Okay, how do you get this rho SP? It's kind of obvious. Go to the table and you can read up these values. For shininess, you come over here. Okay, so you can see that bronze, it has shininess 0.2. If you go for, let's say, gold, it's much shinier than that. It has higher shininess value, 0.4. Okay. Plastics, they have low shininess. Okay. Is this thing clear? Now, to put everything together, we cannot write cos phi. What do? Cos phi is actually dependent on two different vectors. Which two? L? Not L. It's actually N and, oh, not even N. R and V. We know V already. And yeah, this phi. This is over here, right? So R and V. We know R already and V already, so we can write cos phi as R dot V and divide that by magnitude of R, the magnitude of V. So if you put everything together, this is what it boils down to. You can find out cos phi. You can raise the power of that to a certain value and then use that. Okay, so in our next class, since we are right at the end of the class, I'm not going to go with any example. In next class, we will look at a total example with a particular surface, a particular material, how you're going to read these values and put them in together to compute something in the end. Okay. If you want to read this up in your textbook or on the internet, what you'd be looking for is called Phong reflection model. Okay, so when you go back home, I want you guys to look up this thing. It's going to be really helpful for you. Look this up, Phong reflection model, on the internet, or find it out on your textbook. And the stuff that I've talked about, the ambient, diffuse, and specular, all these formulas are already derived over there. You'll see some sample calculation as well. So as a homework, please go through these things. Things will become much more clearer that way. And definitely, these all need a lot of concept from vectors. So you'd have to have a sound understanding of dot product, cross product, and also vector projection. Okay. Any question about any of these things? Alright, so then I'm going to finish this off.